Hello everyone, and welcome to our webinar on maximizing ICP performance for battery analysis. Today we will discuss how to get the best results from your ICP system for battery materials. I will start by covering how to choose the right sample introduction components and share maintenance best practices. Then Ryan will present a case study showcasing improvements in ICP OES analysis of lithium battery electrolytes. Let me start with a quick introduction to glass expansion. With over 40 years of experience, we specialize in designing and manufacturing sample introduction components for ICP instruments. Our products are known for their precision and reliability, supporting laboratories across various industries. We have a global presence with 3 main offices: our head office in Melbourne for the Asia Pacific, a US office for North and South America, and a German office for Europe, Africa, and the Middle East. If you have any questions about today's webinar or future inquiries, feel free to reach out to any of our offices. You can also order our products through our distributors, with more details on our website at geicp.com. On this slide, you can see an overview of our products, from sample probes to cones. Innovation is one of our key strengths. We transform spray chamber design with our cyclonic spray chambers, enhancing sensitivity and reducing matrix effects and washout times. We were also the first to create a fully demountable torch, making component replacement simple and maintenance easier. Our nebulizers are custom-made for optimal performance with each ICP system. Currently, we support instruments from 16 manufacturers and provide solutions for over 50 ICP models. Many of our products are recognized as standard equipment for major ICP systems. Notable innovations include the Micromist and C-Spray nebulizers, along with the patented D-Torch featuring a ceramic outer tube. Now that we have introduced our products, let's look at their role in battery testing. Accurate analysis of key elements like lithium and cobalt, as well as trace impurities, is crucial throughout the battery life cycle, from raw material processing to recycling. Our products are designed to enhance ICP performance at every stage, as each phase presents unique analytical challenges. One major requirement is processing a large number of samples efficiently, which depends on an ICP system with a wide analytical range, since battery materials can vary greatly in element concentrations. Common challenges include complex matrices with high total dissolved solids, organic compounds, and sometimes hydrofluoric acid. These factors require specific adjustments to the sample introduction system. Organic materials can interfere with digestion and ICP analysis, while HF can affect system stability and plasma performance. These complexities can lead to issues like interrupted runs, signal drift, clogged nebulizers, and a reduced torch lifespan. Ensuring optimal ICP performance is key to obtaining accurate results, but it can be challenging since only 1 to 2% of sample reaches the plasma. The sample introduction system is critical, as its role is to produce a consistent aerosol of fine droplets. It starts with the sample probe drawing in the sample, which is then transported by peristaltic pump tubing to the nebulizer. The nebulizer converts the liquid into an aerosol, with the spray chamber filtering out larger droplets. The finest droplets pass into the torch, where the plasma atomizes and ionizes the sample. Finally, the RF coil sustains the plasma, and the ICP-MS cones guide ions into the mass spectrometer. When selecting a sample probe, it's essential to pick one that fits your lab's requirements. The carbon fiber probe is a reliable, traditional option for general sampling, especially with less challenging sample types. However, for more complex samples, such as those in battery testing, where blockages can be problematic, the Guardian sample probe is highly recommended. Its advanced design, featuring a robust tip, and a built-in particle filter effectively prevents clogging, making it a more dependable choice for difficult samples. Additionally, the Guardian probe offers flexibility in accommodating different tube diameters, and the process of swapping between tubes is seamless and user-friendly, unlike auto-sample probes with fully attached tubing. Moreover, its drip-resistant design minimizes cross-contamination during probe movement, further enhancing its reliability for various applications. Proper sample digestion is essential for clear liquids and consistent results, especially for RSDs and spike recoveries. Effective digestion breaks down all components, leading to clear solutions and reproducible data. Ineffective digestion, however, can leave behind precipitates and undigested particles, affecting accuracy and increasing clogging risk in the sample probe. A major challenge in battery sample analysis is clogging from particulate matter in anode and cathode materials. These can block the sample probe, disrupting sample flow and requiring frequent cleaning. Another issue is cross-contamination between different sample types, particularly when analyzing anode, cathode, and electrolyte samples in sequence. Additionally, ionic liquid electrolytes have higher viscosity, which can disrupt smooth flow through the outer sample probe. Here are some easy solutions for dealing with clogging and blockages, aside from pre-filtering your samples. One option is to use Guardian sample probe, which we mentioned earlier. Its drip resistance and built-in filter make it great for preventing clogs. It's also a good idea to set up regular cleaning routines to help prevent cross-contamination. Make sure to rinse between different samples with dedicated solutions to get rid of any leftover materials. To kick off and wrap up each run, try aspirating a mildly acidic blank solution or the sample matrix and then run ultrapure water. Finally, you might want to consider using the Guardian inline particle filter between the probe and nebulizer. This filter does a great job of removing particles from the sample flow, which can help reduce blockages in the sample lines and nebulizers. When selecting pump tubing, you can choose between some of the common materials such as PVC tubing, which is ideal for routine applications involving dilute acid solutions. Solva tubing is the best choice for transferring hydrocarbons and petroleum products, ensuring chemical compatibility. And Viton tubing works great for concentrated acids and corrosive solvents, offering excellent resistance to harsh chemicals. You can also choose between 2-tag or 3-tag options. The 3-tag option allows you to use fresh tubing section as one section wears out, which extends the overall life of the tubing. However, keep in mind that this may increase the time the sample is exposed to the tubing, potentially affecting the analysis of sticky elements. There is also a choice of using a flared-end pump tubing that makes easier to insert larger sample capillary tubing. Finally, when selecting the internal diameter, remember that smaller ID tubing is ideal for precise, low-flow applications, and in contrast, larger ID tubing is better suited for higher flow rates and larger sample volumes, enhancing analysis speed and efficiency. Additionally, the pump speed, along with the diameter of tubing and the cross-sectional area, plays a critical role in determining flow speed, which ultimately influences the sample flow rate. To support you further, we have a pump speed and sample uptake calculator available on our website. In just 3 simple steps, you can easily determine the sample uptake based on the pump tubing and pump speed you're currently using. You can try it using the link provided. Moreover, it's important to note that any variation in the sample flow rate to the nebulizer can lead to signal instability, resulting in poor RSDs. A common issue with pump tubing is wear and tear, caused by constant pressure from the pump rollers. Over time, this stretches the tubing, changing its internal diameter and affecting the sample flow to the nebulizer, leading to inconsistent results. Neglecting pump tubing maintenance can also be a problem. Tubing and capillary lines may become contamination risks if not regularly replaced. To address these challenges, pre-stretching the tubing before use helps improve performance, and keeping proper tension during operation is key. Using Easy Glide cloth to lubricate the pump rollers can reduce wear, minimize friction, and stabilize sample delivery. Another useful tool is the TrueFlow Sample Monitor, which offers real-time flow measurement, preventing issues like blocked nebulizers and worn tubing. Lastly, always release pressure on the tubing when the instrument isn't in use to extend its lifespan. Now let's move on to nebulizers. The most common nebulizer designs are concentric and V-groove. V-groove nebulizers produce larger droplets, which can reduce precision and efficiency. These droplets may not fully dissolvate in the plasma, leading to matrix effects and reduced robustness. Concentric nebulizers, on the other hand, create smaller, more uniform droplets, resulting in a higher transfer efficiency, better sensitivity, and improved precision. However, concentric designs are more prone to clogging when samples contain particulates, whereas V-groove designs handle particulates better. When choosing a nebulizer, consider factors like tolerance to HF, particulates, and TDS, along with the material's purity and chemical resistance. For most battery applications, the C-spray nebulizer is your best option. It delivers excellent performance with high tolerance to the total dissolved solids. However, when dealing with high TDS levels, especially in HF application, the Duramist nebulizer is the ideal choice. Lastly, it's crucial to match the nebulizer to your desired sample uptake rate. For a complete guide on selecting the right nebulizer and matching it to your application, feel free to visit our website, where you will find a comprehensive list of all models and their respective uptake rates. Here we can see the impacts of back pressure and gas flow rates on nebulizer and ICP performance. Optimal back pressure helps create a fine, stable aerosol, improving both sensitivity and precision by ensuring a consistent sample delivery into the plasma. While higher back pressure produces smaller droplets and better results, too much can lead to faster wear of components. For ICP OES, an argon flow rate of around 0.7 liter per minute is ideal for stable plasma and accurate analysis. In contrast, ICP-MS often requires a higher flow rate, around 1 liter per minute, to enhance transfer efficiency and sensitivity. Additionally, the nebulizer gas flow affects droplet size. A higher flow rate generates smaller droplets that fully dissolve in the plasma, boosting sensitivity, while larger droplets may not fully evaporate, leading to reduced performance. So by optimizing gas flow, you improve ionization and achieve more accurate, consistent results. Before we talk about maintenance, let's see how to spot issues with your nebulizer, which can save time when troubleshooting. Many ICP instruments now have a software feature that monitors nebulizer back pressure. It's a good idea to record the back pressure once your instrument has warmed up. This helps you to quickly spot if the back pressure is too high or low. Glass expansions, direct connect, concentric nebulizers work best around 40 psi. If you notice low back pressure and a drop in sensitivity, check the argon gas connection at the instrument and nebulizer gas arm. Over time, the PVC or polymer tubes used for gas supply can harden and lose their grip. Even a small 1% loss of argon can cause noticeable change in your ICP readings. If the back pressure is too high, it could mean that nebulizer is partially blocked. It's also helpful to track your normal sample uptake rate to ensure it stays consistent. A drop in the uptake rate can be another sign of a blocked nebulizer. Also, make sure to regularly inspect and replace the pump tubing. Here are some key tips for maintaining your nebulizer. along with things to avoid. Start and finish each run by nebulizing a mildly acidic blank solution, followed by ultra-pure water. This prevents deposits from forming inside the nebulizer, helping maintain performance and extend its lifespan. It also cleans the spray chamber. Avoid inserting anything into the nebulizer orifice, as this can cause permanent damage. Don't touch the nebulizer tip. Body oils can affect its performance. Never use any HF to clean glass or quartz nebulizers, and avoid ultrasonic baths that can dislodge internal parts. For blockages, use the LO nebulizer cleaning tool to safely backflash and remove buildup. Regular use can improve performance and extend the nebulizer's life. For cleaning, we recommend using a dilute solution of Fluca. Tough clogs might require an overnight soak or cleaning with nitric acid. After flushing with water, methanol can help dry out the nebulizer, but it's not enough for thorough cleaning. We also have a step-by-step cleaning video on our website for more guidance. Next, we have a spray chamber with a profound effect on transfer efficiency, precision, and washout. There are two main types of spray chambers, cyclonic and Scott. Cyclonic spray chambers are the most common because they effectively combine gravity and centrifugal force to filter out large droplets. Cyclonic designs come in a single pass and double pass options. The Twister model has a baffle central transfer tube for smaller particle size and narrow distribution, while the Tracy model offers better transfer efficiency and a 15% increase in counts. Droplet size is crucial in ICP analysis. Mean droplet size is determined in two stages. First, the nebulizer creates the primary aerosol, where droplet size is inversely related to gas and liquid velocity. Then the spray chamber filters the primary aerosol to produce a tertiary aerosol, removing droplets larger than 10 microns. On this graph, we can see that the double pass design has a higher percentage of these smaller droplets compared to the single pass. This is important because smaller droplets improve ionization efficiency and reduce metric effects, while larger droplets may pass through the plasma without ionizing and can contribute to more solvent, increasing metric interference and degrading plasma tolerance. Consistent performance in ICP analysis of battery samples relies on the nebulizer spray chamber interface. Sensitivity can be affected by the depth of the nebulizer and the torque on its seal. The left image shows that increasing the torque can decrease sensitivity by 5%. The latest Helix CT locking screw features a torque control mechanism ensuring consistent sealing of the PTFE ferrule against the nebulizer. It is the only zero dead volume interface which reduces washout time for concentrated samples and minimizes carryover. In addition to maintaining consistent performance, it's crucial to minimize washout time. If you ever wonder why our washout times are so long, check for liquid pooling around the nebulizer seal. We tested this by aspirating a blue dye and found that with a non-GE design, it took over 10 minutes for the dye to fully rinse out. As shown in the right image, the Helix CT washes out a 10 ppm molybdenum standard in just 4 seconds, compared to 16 seconds for non-Helix CT. Now let's discuss maintaining spray chambers. First, never use hydrofluoric acid to clean your glass or quartz spray chamber, as it can cause serious damage. Also, avoid sonication and using metal or ceramic brushes, as they can break the chamber. If you notice washout issues, poor RSDs, or droplets collecting on the chamber walls, it's time to clean. Start by nebulizing a 2.5% Fluca solution for about 15 minutes, then follow with ultra-pure water. If that doesn't help, remove all fittings and soak the spray chamber overnight in a container with 25% Fluca solution. Now let's discuss the torch, which comes in 3 design categories based on how easily they can be disassembled. First, there is the single-piece quartz torch. This is a general option with a lower initial cost, but if any parts gets damaged, you have to replace the whole torch, and it lacks versatility. Next is the semi-demountable torch, which has a removable injector. This allows you to change injectors with different ID sizes. For high salt mattresses, a wide bore injector can help prevent salt buildup, while a smaller bore injector is better for organic solvents. You can also use different materials for specific applications, like ceramic injectors for HF samples. FDT lets you replace the outer and intermediate tubes, as well as the injector individually. The D-torch also features a removable injector and outer tube. The D-torch is a strong, high-performing option compared to single-piece and semi-demountable quartz torches. What makes the D-torch special is the ceramic intermediate tube, which makes it sturdier and more cost-effective. Because of this design, you usually only need to replace the outer tube, the part that wears out first due to stress from samples and plasma. This is especially important for battery samples, which often have tricky mixtures with a lot of dissolved solids. When quartz is exposed to salts and high temperatures, it can break down through a process called devitrification. Now let's review torch maintenance. Always wear safety gloves when handling quartz torch components for your safety. For carbon deposits from organic samples, you can use a handheld propane torch to burn them off the outer tube. Just remember, never heat the D-torch outer tube in a muffle furnace because of the polymer ferrule attached to it. For salt deposits, soak the torch in a 25% solution of Fluca or dilute acid. Stand the tube upright in a beaker and cover the salt deposit with the solution. For metallic films, soak the tube in acid, preferably the same acid used for your samples, again standing it upright in a beaker. Lastly, don't soak the polymer ferrule in acid, as it can be damaged. Proper maintenance is essential for keeping your D-torch working well and extending its lifespan.
Thank you, Maya, for the comprehensive overview of the sample introduction system. Before getting started, please allow me to briefly introduce myself. My name is Ryan Brennan, and I am the president of Glass Expansion, Inc. I have had the pleasure of being part of the Glass Expansion team since 2011. I will be your speaker for Part 2, Innovative Solutions Tailored for Battery Applications. In the lithium battery industry, analyzing organic solvents for trace metal impurities is crucial for ensuring optimal battery performance, but it comes with its own set of challenges. Unlike aqueous solutions, organic solvents are volatile and prone to interference, complicating the analysis. Traditional methods require time-consuming sample preparation like aqueous digestion and large dilutions, which can introduce errors. Additionally, organic matrices can wear down ICP OES sample introduction components, increasing maintenance needs, and the lack of matrix-matched calibration standards makes accurate calibration difficult. To address these challenges, the next section highlights a recent application note developed with Pure Lithium, showcasing an innovative approach for analyzing lithium battery electrolytes in an IPA matrix. In the lithium battery industry, analyzing organic solvents for trace metal impurities is crucial for ensuring optimal battery performance, but it comes with its own set of challenges. Unlike aqueous solutions, organic solvents are volatile and prone to interference, complicating the analysis. Traditional methods require time-consuming sample preparation like aqueous digestion and large dilutions, which can introduce errors. Additionally, organic matrices can wear down ICP OES sample introduction components, increasing maintenance needs, and the lack of matrix-matched calibration standards makes accurate calibration difficult. To address these challenges, the next section highlights a recent application note developed with Pure Lithium, showcasing an innovative approach for analyzing lithium battery electrolytes in an IPA matrix. In this case study, we focused on samples of ethylene carbonate and dimethyl carbonate and ethyl methyl carbonate prepared using 99.5% anhydrous IPA. We use an ICP OES system with a sealed optics, which can measure halogens like chlorine, bromine, and iodine down to 130 nanometers. To ensure we fully broke down the organic matrix, the RF power was set to a higher level of 1700 watts. For those interested in the specifics, a complete list of the ICP OES operating parameters is available in the accompanying table. Now let's turn our attention to the sample introduction components we used in this study. The system includes our C-Spray DC Nebulizer, our Tracy DC cyclonic spray chamber, and our patent-pending Jet Vortex Interface, or as we will refer to as JVI throughout this presentation. Let's first talk about the C-Spray DC Nebulizer. We chose this nebulizer because it does an excellent job handling the complex sample matrix we encounter in battery electrolytes. Its impressive nebulization efficiency is key for getting accurate results. Next up is the Tracy DC spray chamber. Its smaller volume means we can achieve faster washout times, which is super important for maintaining precision in our results. And then there's the JVI. This part really takes our system to the next level by adding an extra layer of aerosol filtration capabilities. This improvement gives us better control over the particle size and helps reduce carbon buildup, which is a big plus. In the next few slides, I'll dive deeper into the features and characteristics of each of these components. The C-Spray DC nebulizer was chosen due to its ability to handle a complex matrix while providing outstanding nebulization efficiency that translates to enhanced sensitivity and precision compared to other concentric nebulizer designs. The unique polished tip enables the C-Spray to self-wash, minimizing the adhesion of salt deposits, resulting in a high tolerance to total dissolved solids up to 20%. The C-Spray sample channel is constructed from Glass Expansion's proprietary Vitricone thick-walled glass capillary, which is precision engineered to the industry's tightest tolerances. This results in an unmatched manufacturing reproducibility and much more durable design compared to other concentric nebulizers. The sample channel is also uniform from entry point to exit, and when combined with a proprietary UniFit sample connector, provides a true zero dead volume sample connection. And finally, we have our Direct Connect gas line, featuring a secure ratchet connection to the nebulizer gas arm and a direct fitting to the ICP Argon gas supply. This completely inert gas assembly ensures optimum gas pressure for optimum nebulization efficiencies. The Tracy DC cyclonic spray chamber is a brand new product to Glass Expansion's popular line of cyclonic spray chambers. The Tracy DC is a smaller volume at 30 mils compared to the standard 50 mil, and in combination with our trademark Helix CT interface, translates to a high-efficiency spray chamber designed for improved transport efficiency and faster washout times. The direct connection feature of the Tracy DC design guarantees perfect alignment to the torch and is completely inert, made from PEEK. Unlike traditional ball joint clamps, the DC connection will not corrode over time. The Tracy DC is also a more cost-effective spray chamber option without sacrificing precision, reliability, or performance. To highlight the washout efficiency of the new Tracy DC spray chamber, we compared the washout profiles of a 1 ppm mercury solution, known to be a troublesome or sticky element. The results are quite impressive, with the Tracy DC spray chamber washout time being 64% faster when compared to a non-Glass Expansion O-ring-free design cyclonic spray chamber. This really showcases the design benefits of both the Tracy DC and our proprietary Helix CT interface. A faster washout time is important for any type of production laboratory, as this benefit translates to a more efficient processing time, less waste produced, and therefore a more cost-effective result. The last product featured in this recent application note is our patent-pending Jet Vortex Interface, or JVI. The JVI was essential to this application as it adds the ability to reduce the average particle size exiting the spray chamber by 3 to 4% for every 0.05 liters per minute flow of argon. In this work, the JVI replaces a high-cost, temperature-controlled spray chamber that would have been traditionally used to cool the spray chamber to temperatures below ambient temperature to allow for the analysis of a volatile organic solvent like IPA. The use of the JVI gas to control transport efficiency decreases carbon deposition and dramatically improves the stability and robustness of the plasma. The JVI is designed to integrate seamlessly with your existing makeup, dilution, or auxiliary gas options for both ICP OES and ICP MS systems, allowing you to fine-tune the size and volume of the aerosol exiting the spray chamber. You can easily adjust the JVI gas flow rate for high TDS, volatile organic samples, or to enhance transport efficiency. It essentially acts as a tunable baffle that can be optimized to your specific sample matrix and application needs. Now let's discuss sample introduction options for cathodes. Cathodes are typically digested in aqua regia and analyzed for high concentration elements such as lithium and nickel, in addition to trace elements. Due to the presence of these concentrated elements and the complex matrix, you may encounter several challenges, including blockages in the sample tubing, nebulizer, and injector, resulting in instrument downtime, increased consumable costs, and frequent maintenance. There is also the risk of carryover and long washout times. To overcome these challenges, we have selected a series of sample introduction products best suited for these types of samples so you can achieve the best performance at the lowest operating cost. The Guardian probe and Guardian inline filter eliminate particulate blockages. The C-Spray DC nebulizer provides the best sensitivity for those trace elements while being able to withstand up to 20% total dissolved solids. This Twister spray chamber was chosen for reducing the matrix load on the plasma and efficient washout of each sample. The D-torch with a ceramic outer tube provides a super torch, able to withstand the toughest samples. And the Allegra Argon humidifier for improved short-term and long-term stability. Since we've already discussed many of these products today, I'll focus specifically on the Allegra and the D-torch with ceramic outer tube. Here we show a perfect example of the benefits of the Allegra. A high-throughput contract laboratory evaluated the Allegra for a lithium metaborate method, comparing the ICP OES signal stability of their internal standards with and without the Allegra. Without the Allegra, the internal standard signal began to drift after just 35 minutes, leading to a failed analysis due to over 10% drift. In contrast, with the Allegra in place, there was virtually no variation in the signal over a 4-hour period. The contract laboratory also reported a significant reduction in the frequency of nebulizer maintenance. Here we show a perfect example of the benefits of the Allegra. A high-throughput contract laboratory evaluated the Allegra for a lithium metaborate method, comparing the ICP OES signal stability of their internal standards with and without the Allegra. Without the Allegra, the internal standard signal began to drift after just 35 minutes, leading to a failed analysis due to over 10% drift. In contrast, with the Allegra in place, there was virtually no variation in the signal over a 4-hour period. The contract laboratory also reported a significant reduction in the frequency of nebulizer maintenance. A major challenge we face with high lithium concentrations is the rapid degradation or devitrification of the quartz torch, specifically the outermost tube, resulting in frequent torch replacement and high consumable costs due to the short lifetime. With a demountable torch design, you can reduce that cost by replacing the torch body. However, with Glass Expansion's patented D-torch design, you can reduce that cost even further by only having to replace the outer tube. With the D-torch, you also gain the benefit of an optional ceramic outer tube, which, as we mentioned earlier, can withstand the toughest sample matrices, including high salts like lithium. Ceramic, compared to quartz, does not devitrify or suffer from sudden temperature fractures. Ceramic outer tubes have a longer lifespan, significantly reducing maintenance, cleaning, and downtime. Ceramic outer tubes even provide a higher average signal intensity, especially when dealing with high matrix samples, as they maintain a hotter and more robust plasma. Additionally, to note, a 2.4 millimeter or 1.8 millimeter ID alumina injector also works well with these challenging sample matrices, providing a longer life compared to quartz, and the larger bore resists salt accumulation. In the final section of today's webinar, I will recommend products for the analysis of battery samples that contain or use any concentration of hydrofluoric acid. As an example, in cathode recycling, the residual electrolyte can decompose into hydrofluoric acid during the leaching process. Additionally, when working with lithium hexafluorophosphate, an electrolyte solution mixed with ethanol and carbonate-based aqueous solvents, we need to be mindful that this can also produce hydrofluoric acid in an aqueous solution. To address these challenges, you must employ HF-resistant sample introduction components. Our recommended products for a high-performance inert sample introduction system would include the Duramus DC Nebulizer, Tracy DC Peak Spray Chamber, fully ceramic D-torch with an alumina injector, and Solvaflex pump tubing due to its chemical compatibility with both organic solvents and hydrofluoric acid. Earlier today, I introduced Glass Expansion's new Tracy DC spray chamber design. Like the glass version, our new Peak Tracy DC spray chamber features the same high-efficiency 30 ml volume design and direct connection to the torch. The raw material, Peak, is resistant up to 5% hydrofluoric acid and provides excellent wetting characteristics. This material helps to retain the wetting properties of the internal surface of the spray chamber, even with repeated exposure to challenging samples, as long as regular and proper maintenance is followed. Unlike our PTFE and PFA cyclonic spray chambers, the Peak Tracy DC does not require the proprietary steady flow surface treatment to match the analytical performance of a glass or quartz cyclonic spray chamber. This simplifies maintenance and reduces the ownership costs of the Peak Tracy DC cyclonic spray chamber. As we conclude this webinar, I'd like to remind you of the wealth of valuable resources available on the Glass Expansion website. These resources are completely free and include other webinars, application notes, product information, and much more. You can also search for recommended products that suit your specific ICP OES or ICP MS model, in addition to what your application is. If you have any questions or need further assistance, please do not hesitate to reach out. Glass Expansion has a great team of technical experts who are here to support you. Thank you for your time today. Maya and I hope you enjoyed the webinar. Before we conclude, I have shared the contact information for each Glass Expansion office. Should you have any questions, you know how to reach us for support.